We'll continue today with electric motors. Right now we're still on the DC motor. If the sparks you couldn't see in the last lecture were captured beautifully on the video that you can see, but you can imagine what they look like, teeny little sparks. And I mentioned that this is actually one of the largest disadvantage, probably the largest disadvantage of the DC motor for three reasons. I'll just recapture them. The first reason is there is some wear, because as the brushes slide, there is wear, mechanical wear, and the sparks themselves cause electro-erosion. Electro-erosion is like a wire EDM machine, that whenever you have sparks, some minute amounts of metal is vaporized, just like an EDM machine works. So it actually removes a bit of the metal, so there is wear. There is a bit of loss of energy, and I mentioned that every spark represents some energy, because the sparks are actually miniature transmitters of electromagnetic energy, and so and another way of looking at it, there is some stored energy in the coils, Li, half Li squared, and if the brushes short out the coils, even for a very short time, some of this energy dissipates. And the third reason, which I mentioned today is the largest reason, is today everything is wireless, so people don't like sparks, because sparks is transmitters, it interferes with the spectrum. And in the old days, when electric motors were invented, there was no such thing as radio. So people just looked at the sparks and they said it's cute little blue light. Didn't bother anybody, right? But today, just the fact that everything is wireless and there's a lot of highly sensitive detectors, and they are also subject to interference even if they are not wireless. For example, you go in a hospital, you cannot use your cell phone just because there's a lot of highly sensitive piece of equipment. So because of that, the DC motor is not used as large industrial motors, but it's used a lot of small motors, because in a small, if the motor is small, also the amount of RFI or EMI is small. EMI is electromagnetic interference, and it's easier to shield the motor if you really want to get rid of the noise. And it's still one of the best motors as far as characteristics, and that's what we're going to discuss today. What are the characteristics of a DC motor which make it so desirable? And most of you don't even realize how popular this motor is, because when you look at things, you don't realize that everything is full of electric motors. Like even this desk, there's a way I can move it up and down, that's a DC motor. Okay, if you look at a car has one big engine, but a modern car has about a dozen DC motors. And you don't stop and think of it, but when you think of a car, you have power windows in most cars, so that's 4 motors. Okay, you have a windshield wiper, sometimes front and back, so there's already 6 motors. You have a fuel pump, most cars now have electric fuel pump, is 7 motors. Now you have a fan in the car, it's 8 motors. Now if the car has power seats, it's another 4 motors, so it's already 12 motors, okay? And if you keep thinking, you'll find a few more motors hidden somewhere in the car, okay? So even a thing like a car, on the average, a car has, I would say, 10 electric motors. So these DC motors are everywhere, and in of course, power tools, some appliances, all the kitchen appliances, not all, but many of the kitchen appliances, like mixer, blender, these are all DC motors. So what is it? Today we have other motors. We have induction motors, we have synchronous motors, which we'll discuss next week, or maybe this Thursday already. But what is it about the DC motor which makes it so popular even today when there are other choices? Because the cost of building a DC motor is actually very similar to the cost of building an AC motor. Because when you look at the motor, all motors have a rotor and a stator and some coils. And to make a full motor, it has a cover with bearings. So basically, it doesn't look any cheaper than AC motors, which we are going to discuss later on. So what makes the DC motor so popular? So to understand that, we have to derive a little bit of the equations of a DC motor, and very, very elementary equations to see what makes it popular. So when you look at motors, there is a universal way to looking at a motor and deciding what good is it, and the universal way is to plot on one axis to plot the speed, and on one axis to plot the torque. Okay, so this will be RPM or any other units that you want, and this would be torque. Okay, so most people think about it and say, what would be the ideal motor? A lot of people say, well, an ideal motor would be a motor which holds the RPM constant up to its maximum torque. Okay, actually synchronous motors, which we haven't discussed yet, they have this curve. But then you think about it again and say, is this really the ideal motor? So if you want some applications where you want to minimize power, energy loss, weight, is this really the ideal motor? Because power in a motor, of course, is T times omega, where omega is proportional to RPM, right? Torque, T is torque times angular velocity. So if you have a motor like that, then at very low speed, it actually has very little power coming out. But if you think in most applications, you actually, at low speed, sometimes you need, at low speed, this way, at very low speeds, the torque times omega becomes very low, because if the speed goes to 0, the torque times omega, the power coming out of the motor, goes to 0. Okay? So what kind of curve would you really like to have in most applications from a motor? So you start thinking about it and you realize you want, if your motor can output a given power, you really would like to have a curve like this, basically a 1 over x curve, because in this curve the power is always maximized. If this is torque and this is RPM, if you have a low RPM you get a very high torque, if you have a high RPM you get a low torque. But if this graph is hyperbolic, so basically this graph is torque times RPM, or torque times omega is constant. Okay, so basically RPM is 1 over torque times a constant. Now this graph is actually much better for most applications, because at any point of the graph you are utilizing the maximum power of the motor. Okay, and then you start thinking about it a little bit more, and you say, of course, because that's what a gearbox does in a car. Right? Because why do cars have gearboxes, manual or automatic? Because in a car, the car engine only has a certain horsepower, unlike an electric motor, which can momentarily be overdriven. Like in actuators, an electric motor you can drive for a very short time, a huge power through it. Okay? Unlike this internal combustion engine, you cannot overdrive it much. It has a certain displacement, you can inject full fuel, full air, but you can't inject for a tenth of a second 10 times the fuel, 10 times the air. It wouldn't work, okay, because it just can't breathe, can't pull in enough air for the combustion, so on. So in a car, what you do, you change the gears. If you want to go uphill, you need a high torque at low speed, you switch the gears, so you work here, and you work here. If you want to go very fast, you work here. So basically, if you had a motor which has a characteristic like this, you wouldn't need a gearbox. And many things have gearboxes just to match the load to the motor. Okay? Because you always, to make the lightest car or the lightest hand drill, you want to use the maximum power of the motor. And to use the maximum power of the motor, you have to match the load to the characteristics of a motor, typically by using a gear. because a gear conserves the power, it just matches, so to speak, the impedance. So if you think in terms of electrical engineering, a gear is an impedance match, because there is something which wants to work at a certain speed, a certain torque, like here, but you have a motor which works here, so you have to use a gear. You keep the power constant, but you match the load. So it turns out, as we'll see in a few minutes, that if you take a DC motor and you connect it in series, not in parallel, it has this curve. If you connect it in parallel, it has this curve, or almost this curve. So basically, by taking the same motor, and depending how you connect it, you can get this curve or any curve in between, actually. And that was very, very important in the days where there was no electronic, where you could easily do PWM and switch and do control things, which today you can. But even today, with electronics and PWM and everything, this is very, very desirable, because the motor already comes like this. You don't have to waste money or power to make it look like this. Okay, so let's go over it and see why. So we'll start with PMDC motor, which is the same as this motor because the field was connected straight to the battery. So if I take an electric motor, if I have two magnets, north, south, and I put a coil with a commutator in between, or, and this is a coil here, this is a coil, the winding, okay? So if I have this type of motor, or I replace the magnets, I still have the coil, and I replace the magnets here by two other coils, but if these two other coils are connected to a battery, they are the same as a permanent magnet. So there is no difference between a PMDC motor and a motor that instead of a permanent magnet, you're actually using a coil and a battery. Okay. Now, if this is the same battery which also powers the commutator, then there is a bit of a difference, because when you change the battery voltage, the field also changes. If this is a separate power supply, a separate battery, it's exactly like a permanent magnet. Good. So what characteristic would this motor have? So when the motor starts turning, it's moving a conductor in the magnetic field. So every conductor in the magnetic field generates a voltage. So the equation of this motor is not as simple as if this is a voltage. So if I draw it again, if I draw this thing larger, so if I have here the coil, actually I draw it the way we drew it before. We have NS, we have a magnetic field, and we do a cross section here. Here is a conductor, say current going in, current coming out, and here is a commutator. The commutator in this way should be drawn like this, and these are the brushes. Okay? So if I draw it this way, there is a coil wound on the armature, actually connecting the brushes, which is this coil. Now, let's say there's a voltage V. I connect this to a voltage V. So the current is not simply V divided by R. If the motor was stationary, in other words, if I jam it, in a connected battery, the current will simply be V over R. But the moment the motor rotates, each conductor acts as a generator, okay? Because the conductor is cutting through a magnetic field. So the conductor itself, by moving the magnetic field, generates a reverse voltage, and this reverse voltage is called back EMF in motors. Okay? Okay, that's a electromagnetic force, but that's a term they use. It's actually not a force, it's a voltage, but that's a term they use for the voltage generated by the conductors. Okay? So the real equation is I is V minus the EMF divided by R. So The EMF is only generated when the motor is rotating. So if the motor is stalled, this term disappears, it's V over R. Okay? But as the motor is rotating, there is a back EMF which limits the current. Okay? Now, if we want to put it in equation, we know that the EMF, we know that it's proportional to BLV, because any conductor through a magnetic field generates a voltage BLV. Now we can actually do a full analysis, but at the end it doesn't matter because we just call it by K. So say if these conductors are lengths L, if the conductors are lengths L and there are N of them, and the radius is R, okay, and the field is B. So we can do a exact analysis, but it's not very important because, as I said, at the end we don't care, we just call it K. So the exact analysis would be if this is omega, if the rotational frequency is omega, the velocity here is omega r. So in the formula BLV, okay, V is simply omega r, L is N times L, because we have N conductors, each one length L, okay? And we actually have two of them, because this generates a voltage and this generates a voltage. So it's actually, so it's 2NL, and B stays B. So if we want to work it out exactly, it is 2BNL omega R, but we really don't care because we just call it capital K times omega. Okay? Because this is all parameters of the motor. All these things except omega depend on the construction of the motor. So if we rewrite this, we get I equals V minus K capital K times omega divided by R. Okay? And okay, we also know that the torque of the motor, yes please?
Sorry, can you explain why it's 2NL for L?
Pardon?
Why is it a factor of 2NL?
Because we have the conductors here, but if you look at the motor in 3D, there is a loop which goes like this. This is L, but there is also a voltage generated by the lower part of the loop, and the two voltages are in series. Right? Because if you look at the directions, these two add together. So it's 2L. But it doesn't really matter, right? Because the real derivation could be different because these loops can be not square, but all what matters is it's a constant times omega. Okay, so this is okay. Now this K is known as a voltage constant of a motor. So if you look at a data sheet on a DC motor, it says like resistance, current, usually it says voltage constant. Usually they give you in the data sheet, K is given by volts per kilo RPM. For small motors, for thousands of RPM. So usually it say like K will be, for example, will be like 2 volt per 1000 RPM or something like this. That's how the data sheet gives this K, the K. Now, if you look at the torque of a motor, you realize right away that the torque this motor can generate for a current I is actually a very similar formula, because each one of those, if there is a current I, the force will be BLI. So now I'm deriving in a similar way the torque. This was deriving the current versus voltage, but now I derive the torque. So we know the torque in general is BLI, and in the case of the motor, it will be, this is a generic formula, so in the case of the motor it will be B, instead of L it will be 2L times N, okay, times I. Because the same reason, the reason it will be 2 times R, sorry, so, times, if I have to multiply by the force, just it's better to write it like this. Force is BLI, and torque will be the force times the radius, times this times the radius. So this will be the torque. And it will be 2L, because each arm generates its own force, and the two arms work together. So it's very much the same derivation. The torque of a motor will be the same thing as here. It will be 2B N L times R, all this times I. So all this we'll call K, and if we look at this K, we'll see that actually numerically it's equal to the voltage K. Okay, so surprisingly or not surprisingly, it depends how much you think about it, the torque constant of the motor is K times I, but it's the same K as the voltage coefficient. Okay? Good. So, okay, so these two are the main parameters of the motor. So the same K, which is given as volts in kilo RPM, is also a Newton meter per amp, assuming they normalize the units, right? Assuming it's, because RPM is not RPM is not an MKS unit. So you'd have to convert this to radians per second, right? Because RPM you have to divide by 60, multiply by 2 pi, so this will become radians per second. So if you, is everybody clear on that? Once you converted this to radians per second, you'll get a different K, but this K will be the same K as Newton meter per amp, the torque constant of the motor. Because if you look what this K contains, it contains exactly the same elements. Okay? So the short of the story is, for a DC motor, there is something called K, which is both the voltage constant. So if you use the motor as a generator and you rotated it at certain RPM, this will tell you how many volts you get. Okay? And the same K will also be the torque constant. If you gave the motor 1 amp, you'll get a certain torque, and the torque will be Ki, it's the same K. Okay? Good. So now, okay, so we can rearrange the equations to generate these curves, but first let's look at it intuitively. The first moment when we connect a battery to the motor, the first moment we'll get a very high current because there is no back EMF. We'll get V over R. But as soon as the motor starts turning, we'll get this current. Okay. Now, when you make the motor, you're trying to make it as efficient as possible. So you're trying to make this resistance as low as possible, because this resistance represents losses. So I'm thinking a way of seeing it here. If I multiply both sides by voltage, okay? So I'm going to get here V times I is a power. I'm going to get here V squared over R, okay? And I'm going to get voltage times this. So this part represents actual power, this part represents losses. So a better way to visualize it is we draw the electrical circuit. We have a battery V connecting to the motor. So a better way to visualize this is we draw, this is the internal resistance of the motor, and this is an opposing battery, which is a back EMF. So this is a back EMF, which is a voltage generated to oppose this battery, and it goes up with the speed. Okay? Now, this power, I squared R, This is simply losses. If R was 0, it would be better, because this does not put any power. Now this power, the back EMF times the current I, is actually the output power of the motor. Because this what does the work, because if you have a current I, you have a torque Ki. Okay? And if you have a torque Ki, and you multiply it by the RPM, you get the power. So the current I generates a torque, and if you have a current I at an RPM omega, you generate a certain power. So because of this, when you build a motor, you're trying to make R as low as possible. Sometimes it's good to have a little bit R, otherwise it'll be a complete short when you turn on the motor. In any case, you can't actually build it with no resistance. But if you could, you would build it with no resistance, and you will start it with a very low voltage. So as soon as it starts spinning, you get a back EMF. Okay. Okay. So if you look at this equation, if you look at this graph, okay, it seems that if you took a motor like this, let's say with no load, first we'll take it with no load, for every voltage it will spin at a certain speed until the back EMF equals the voltage you apply. Because if you look at this model, if you had no resistance, the back EMF has to be equal to the voltage, okay? And the back EMF is simply some K times omega. So this is K times omega. I'll just erase this. Just erase this so you can see it. So the back EMF, as we proved before, is K times omega. Okay? So if you had no resistance, for every voltage, the motor will spin at omega until this voltage equals this voltage. Because if there's no resistance, if the voltages are not equal, the current will be infinite. Because you take two batteries together with no resistance, the current is infinite. If the current is infinite, it will generate infinite torque. And the infinite torque will immediately correct the speed. Okay? So do you understand it intuitively why if you change the voltage, the RPM has to change? Because the RPM generates a back EMF, and if there's no resistance, it's like another voltage source. So the voltage sources have to be equal. Okay? So if they're not equal, current will be infinite, torque will be infinite, it will match. So if I draw now, if this is RPM or omega or RPM, which are the same things, just different units, and this is torque, and if I apply V1, I'll get a curve like this. Regardless of torque, at voltage 1, it will have this speed. Now the reason why it will be regardless of torque, because if there is really no resistance here, if I try to lower this EMF, the current will become infinite again. So regardless of torque, this voltage has to be equal to this voltage. Okay? Sometimes it's more visible if I take this top equation and rewrite it, and then it becomes more intuitive, because I can rewrite this equation as V minus K omega equals IR, and therefore omega, it's omega, so omega equals V minus IR divided by K, and in this form it is a little bit more intuitive. So if there is no resistance, then the omega has to be V over K, has to be constant. Okay? So this is V1. If I give it another voltage, it will be V2. Now, because there is some resistance and the current goes up with a load, okay, then if I increase the load, the IR will start increasing, and I'll get a drop, because from here, this was torque. The torque of the motor was Ki, so again we can rewrite this equation that I is torque over K. Okay, so if I increase the torque, the I will increase by this ratio. Okay, so if I increase the torque, the I is increasing, and instead of getting simply V over K, I'll get a straight line like this, where the drop is simply IR, okay, but I is torque over K. Okay, so let's rewrite it in this form, and then it will become clear. So the basic equation of the PMDC motor or parallel wound motor, the basic equation is omega is V minus IR divided by K, but we already know that I is torque divided by K. Okay, so we can rewrite it V minus torque divided by K times R divided by K. Okay, so now we have a direct relationship between torque, omega, and V. So now we can plot a family of curves. Using this relationship, we can plot a family of curves. So if there is no torque, simply the curves will look like this. This is torque and this is omega. If there is no torque, the curves will just look straight lines, V1, V2. Each one will be simply V over K. The moment you add torque, it starts reducing V by a factor of IR. And it's linear. If I double the torque, I'll double the drop. Okay? So it all becomes a first order linear equation which looks like this. Okay, so this is ideal. R equals 0, and this is with a real R. Okay, but you can make this R very small, and matter of fact it is very small, because if you look at DC motors, that R is actually a very, very small portion, and the reason I know that, because I know that motors are highly efficient. Typically a DC motor, a big one is 90% efficient, a small one is 70% efficient. So I know that this term has to be much smaller than this term, because this term represents the losses, and this term represents the work. Okay? Is that clear intuitively to people? Okay, good. So because motors are efficient, I know that this drop, which is the IR drop, has to be very small compared to the voltage. So because of that, the curves yes?
Why is the slope is R?
Pardon?
Why is the slope is R?
No, the slope is not R. This is with R. This is a motor which has no R, R equals 0, and this is a motor which has R. The slope is not R. The slope is this. The slope is this. Okay? Or the function of torque. This divided by K is the slope. Okay, but this is a motor but the important thing is that this drop is actually very small. Say for a really big motor, like an industrial motor, it will be almost no drop at all, because these motors are very efficient. So the R is very small, the drop is very small. So in a nutshell, a PMDC motor or a motor which has a field which is connected to constant voltage looks like this graph. It's more or less constant speed, actually has a bit of droop, and if you change the voltage you get a family of curves, which also shows you how you control the speed. To change the speed you just change the voltage. Good? Okay. Now what happens if we don't connect the field and the armature in parallel, or if we don't use a permanent magnet? So let's look now Okay, what happens if we take a motor like this? Same motor as we drew before, but instead of a permanent magnet, we connect it like this, and we connect the battery here. So what we are doing, and this is the armature, and this is the coil of the armature. This is a commutator. These are the brushes. Okay, so what happens if we wire the armature in series with the field? Okay? Okay, so now something interesting happens. When you start the motor, the first minute you start the motor, there is no EMF. So if we call this R like before, and we call this R1. Okay, so when we start the motor, I equals V divided by R plus R1, and this is when omega equals 0. This is when we start the motor. So when you start the motor, there is a fairly high current, which means the B is very strong, because B was a magnetic field generated. This magnetic field is proportional to I. Okay? Like any electromagnet, B is proportional to Ni. Okay? Or B is proportional, let's call this N1. So B is proportional to N1I. So when we start the motor, because there is no EMF, there is a very high current, there is a very high B. Now, if there is a very high B, there is a very high torque constant, because when we derived K, which is also the torque constant, we said that K was 2N LR B times B. Okay, that was a K. Okay, both the voltage constant and the torque constant. But we assume B is a constant. For a PMDC motor, B is a constant. It's a permanent magnet. Or if it's connected to a constant voltage, it's a constant. But if you connect the armature in series with a field, B is no longer a constant. Okay? So, and what happens, so what is changing now when we look at this equation? That K in the equation is changing constantly, because that K becomes actually a function of I. Okay? So, I mean, you can plug one into the other and derive the equation, but it's more important to understand it intuitively. So if you take a PMDC motor, like this, the motor we dealt with before, we said if we increase V, the motor runs faster. Now what happens in a PMDC motor if we increase B? Let's say we replace the magnet with a stronger magnet. Will the motor run faster or slower? Okay, that's the key to see if you understood how a motor works. So you have a permanent magnet motor with N and S, and an armature with a battery running the armature. Now you increase B by changing these magnets to a stronger magnet. Let's say the motor has no load. So if you increase this magnet to a stronger magnet, will the motor run faster or slower? Bad. No, slower. Okay, the reason it will, and so I'll go over it again, because as I said, the equation is one thing, but the intuitive understanding is something else. Okay, so if I increase B, the voltage constant will become bigger, because the voltage constant was this. So if I increase B, K becomes bigger. Okay? Now, if K becomes bigger, the voltage if K becomes bigger, then the armature has to turn slower to generate the same voltage. Because if we look at a simplified motor is a battery and a back EMF, and this is simply K times omega, and this is V. If I make K bigger, omega is slower to match the V. Is that clear? I mean, the motor also has a small resistance, but the resistance doesn't really affect the answer much, because the resistance IR is small compared to V. So look at this picture again. This is a battery I connect to the motor, and this is a battery which is formed by the back EMF, the motor rotating. Okay? If I make K bigger by increasing the magnet, omega will have to be slower, so the product will stay V. Is that clear now to everybody? Okay, so keep it in mind that contrary to your intuition, if you take a PMDC motor, you make the magnet stronger, the motor slows down. But it has more torque, right? Because the K is also, the torque is Ki, so for the same current, it has more torque. Okay, so in a PMDC motor, B is constant, so we don't have to think about that. But if you connect the motor in series, K is not constant. So at the beginning, when the motor just starts up, the currents are very big, motor has a lot of torque, but low speed. Now as the motor speeds up, the current goes down, because the current, once you have already back EMF, the current is simply V minus the EMF. In this case, not divide by R, but divide by R plus R1. Okay? So as the motor speeds up, the current goes down. Now, as the current goes down, B goes down. If B goes down, K goes down. If K goes down, the motor has to run faster and faster. Okay? So theoretically, if there was no air resistance, the motor will run up to self-destruction. Okay? So you can plug in the numbers. If you want to see the equations, it's easy to plug in the numbers, but the important thing is to understand it intuitively, that the current which is forming B is basically just the difference between the voltage and the EMF. Okay? If the motor has no load, the EMF is trying to catch up with the voltage, because it goes faster and faster until the EMF catches up with the voltage. If the EMF catches up with the voltage, the B becomes near zero, because the current becomes near zero. If this equals to this, the current is zero, the B is zero. If the B is zero, K is zero. If K is zero, then omega, okay, is infinity. Okay? So what happens, you get a behavior which looks like this. Okay? You get a behavior which looks like this. If this is, again, this is omega or RPM, whichever unit you want, and this is torque. At very high torques, okay, at very high torques, you have high currents, because we know that torque is Ki. So if you have high torque, you need high current. Okay, never mind that K keeps changing in this design, but at the higher the torque, the higher the current. So if the current is higher, the K goes up too, so the motor doesn't have to turn fast to generate the back EMF. Okay, so at high torques you have high current, and you work like here. At low torques, you get a low current, then you get a low K, and if you get a low K, the motor has to turn very, very fast to match the voltage. Okay, you get this. So if you derive the equation, you'll get this. Now, if you want to derive the equation, it's very simple. All what you have to do is to fully derive the equation. All what you have to do is substitute, instead of a constant k, you substitute k as a function of current. So the original equation was omega. The original equation is here. Omega is a voltage minus T over K times R divided by K. But now, instead of K, you put in a K which is a function of current. Okay? So let's say that now, let's say that K is some other K, let's call it small k times I. Okay? So you plug this k here, and then you get an equation which leads to this graph. Okay? So it's not so important for me that you derive the equation. It's important for me that you understand intuitively that in this kind of motor, at high loads you get a high current, and at a high current you get a high B, and at a high B you get a large K, which matches the load. At low loads, as the load goes down, the current goes down, B goes up, so the motor has to run faster and faster. Okay? So because of that, you get a motor which adjusts itself to the load. Because let's say you take this motor and you apply a very heavy load. If you apply a very heavy load, then the EMF initially is 0. The motor barely rotates. The EMF is 0, and if the resistances are low, you'll get a huge torque, because the initial current will be very high, will be V over R, and R is very small. Initial current which is very high will generate a very high B, because B is Ni. A very high B will give a very high torque constant. So the motor will be able to start against a very big load, because the torque constant of the motor, the torque, which is Ki, okay, not only I will be high, but K will also be high. And K is proportional to I, so the torque will be proportional to I squared. Because if K is constant, the torque is Ki, but if K itself is a small k times I, then you get the torque looks like Ki squared. Okay? If you ignore resistance. Okay? So because of that, if you apply a very big load to this motor, not only is the current which is going to flow is going to be big because the EMF is small, but the motor will adjust and develop a very large torque constant. Okay, if you apply a very light load to this motor, the current will be low. So the current will be low. The K in the voltage equation will be very low, so the omega will have to be very high, so the back EMF matches the input voltage. Okay, so this motor is called a series wound, or sometimes called universal. Also called okay. Now, yes.
Sorry, so is it the air resistance that stops the transmission?
Yes. The only thing which stops a series wound motor from exploding is the air resistance. And actually, these motors can run at dangerously high speeds. Okay, because if the motor was designed to drive some load, and you just turn on the motor without the load, and a big motor, it will explode to pieces. Because in a big motor, the motor has a lot of torque, and the air resistance is not so big. So you have to be very careful with these motors. A good example where you can see this behavior if you use a power drill, a power saw, or a router. When you start using the router, when it's not cutting the wood, it runs at 30,000 RPM, because you can hear it has a very high-pitched whine. And as soon as you start cutting the wood, you can hear it slow down. Because when you start the router, there is no load. It's running here, and it's designed that the air resistance would limit it to 30,000 RPM. And as soon as you cut, it moves down here. A drill is designed that it doesn't run so high. Okay? But especially in the router, you can hear the sound change as you cut the wood. Yes?
Is there some danger at that moment when you put in the load, like in the transient?
No, because it's a continuous curve. The moment there's a bit of load, immediately the speed will go down. But if you do the math, which I'm not going to do the math right now, but if you do the full math, you find out that if there was no resistance, it was exactly a curve of constant power. If there was no resistance, this curve would be exactly omega times t equals constant. Okay? So there is nothing happens. It just moves up and down on this curve as the load changes. And if just like when you had the PMDC motor, and the PMDC motor had a curve like this, it just moves up and down the curve as the load changes. But here it moves up and down the curve and the speed is almost constant. Here it moves up and down the curve and the speed can change 100 to 1 depending on the design of the motor. But this is very desirable because this is like having an infinite automatic transmission. So think of it, the purpose of an infinite automatic transmission is to generate this curve, so that you can always get the full power out of the motor. Okay, in a car, say. But if you have a DC motor, that's why these motors were very popular in early electric cars. Today they're using synchronous motors or induction motors for other reasons, mainly of commutation. They don't want the sparks. But if you made a simple electric car, like a golf cart, this was ideal motor because it always gives you the maximum power. But you have to be careful because you don't want the car to run at infinite speed if there's no load, like downhill. So you have to limit it. Now the way you limit it, there are many, many simple tricks to limit it. Can somebody think of a trick besides air resistance to limit the maximum RPM here? So if I look at that, if I look at this, the way I drew it, if this voltage, if the EMF will match V, the current will drop to 0, the K will drop to 0, the speed will go to infinity. Okay? So what can I do? A very simple thing which will somehow limit the K from dropping to 0. Because this K here depends on having a current. If the current drops to 0, there will be no K. So what can I do? Yes?
You can add another coil around the...
Excellent idea. All that I have to do is either add a little coil which is connected in parallel to always maintain some B, or I can just put a resistor. What I can do, which is sometimes even simpler, I can, even if I put a very small resistor across this, so if I put a very small resistor from here to here, some current will always flow here. So even if the omega matches, the EMF matches V, there'll still be some B left. Or I can use a bit of permanent magnetism. Okay? So such motors, which are series mount, but maybe have a second coil or a second trick, a magnet, to limit the K from going to 0, these are called compound. So I'll draw this. So the big industrial motors, because of the fear that the speed will go to infinity, are always actually designed as compound. So let's draw it schematically. So this is a field, and this is the armature, and these are the symbols typically used in motor diagrams. So this is the armature. So this is a pure series motor, okay? But in industrial motors, you tend to add a second field, a second coil. Okay, so this will be the main field. This is the main current is going through this. But you add a second coil in order to prevent the B from going to 0. So such a motor is called compound wound or compound. And this is typical of big industrial motors. But the little motors that you have in your router or drill press are just like this. Okay? Now another interesting property of this motor, what happens if I apply AC instead of a battery? Will it run or not? So in PMDC, just as a reminder, in PMDC we already decided last week that it wouldn't work with AC, because on one half cycle it will try to turn one way, on the other half cycle it will try to turn reverse, right? So it just vibrate, okay? But what will happen in this motor if we applied, or in this motor here, which is the same motor, if we applied AC? Will it rotate or not? Yes, and why? Because both switch together. If this is N and this is S and they attract, if the cycle reverses, this will be S, this will be N, they still attract. Because they're in series, they both switch together. Okay? Okay, now a very subtle question. So the series wound motor can be run on AC, and I already mentioned last week that the parallel motor, if you use a coil instead of a permanent magnet, if we take a PMDC motor, but instead of a permanent magnet, we use a shunt wound motor, we said it can also run on AC, because the same argument. When this switches polarity, if I have a sine wave, when it goes to the negative half, both switch polarity, so the force stays the same direction. So both this one in theory can run on AC and this one can run on AC, but when you take apart power tools, it's always like this. So first, because the desired curve. But there is a second reason. Even if you didn't need this curve, if you just wanted a motor to run on AC, you will find out experimentally that the series wound motor runs much better on AC than this motor. And matter of fact, you never see this configuration used on AC, even if you want constant speed. You don't see this configuration. So now this is a very subtle question. Can somebody guess both this motor and that motor can work on AC by the polarity reversing together, but this works much better. Can somebody guess why?
Do you get lagging current from the two inductors?
You're very, very close, but why wouldn't you get it here? You also have two inductors in series. In both cases you have two inductors. Here you have two inductors in parallel, and here you have two inductors in series. But why somehow this works much better? What's wrong with that? Like in DC, it's also in parallel. No, that's a subtle question. You really have to understand electrical engineering to answer that. Yes?
The voltage phase is the same, but the current phase is off. They're on both.
Excellent. You must be electrical engineering student. See, good. Because when you have two inductors, and the two inductors have resistance, so this is the DC model, but if I draw the AC model, okay, if I don't just look at the currents, but I look at the phase shift, so each one has a resistance and an inductance, but the exact phase depends on the ratio between inductance and resistance, because if you recall from electrical engineering, what happens, there is IR and there is J omega L or I omega L, okay, and the resultant vector is actually the phase. Now when you have different ratios of inductance and resistance, you have different phases, so the magnetic poles don't switch together at the same time. There is a small phase shift, because if this is a different L over R than this is R, this is L, this is say R1, L1, and the vectors are not exactly parallel because the vector is depending on the ratio between R and L, right? So now that theory that both phase switch at the same time is not exactly correct, because one will be like this and the other one will be a bit out of phase, so the power, which is a product, will be I1, I2 cosine phi. Cosine phi is a phase shift. But if they're in series, you are guaranteed that the magnetic fields will always be in phase, because it's the same current. Clear? So that's why for AC you always use a series configuration. Okay, so I'll give you a quick demo. We'll go over it one more time on Thursday, but right now I'll just give you a quick demo. So I'll come back to where we were last time. So this is wired in parallel now. So if I run it at different voltages, it will run at different speeds proportional to the voltages. Okay, so I have 3 batteries here, so I can run it at 1.5 volt, in which it probably wouldn't do anything. I'll hold it up so you can see it. Okay, so at 1.5 volt it probably wouldn't run at all. Maybe if I help it, it will run. So it goes very, very slow. Okay, if I double the voltage, in theory it should double the speed. It will be a bit more than double because it barely could move. The friction stopped it from moving. So if I double the voltage, it runs at this speed, and you can hear it reaching a steady state speed. It starts and reaches a steady state speed. If I triple the voltage, again it will ramp up and reach a steady state speed. And after a second you can hear the speed is constant. Okay, now I can take the same motor and just connect the 2 windings, this to in series instead of parallel. Notice this is a battery, the brushes are connected in parallel, so now I'll just take it and rewire it for series. So it'll be like this. Okay, so the battery, yeah, it's like this. So now what's happening, the battery is going through one coil, and coming out of this coil it's going through the commutator, and then I connect the battery to the other side of the commutator, so the motor is wired in series. Okay? Okay, so what limits it here, it's not going that fast, because not so much because of air friction, but because of mechanical friction. I mean, that's quite an inefficient motor because it has big air gaps. So it's actually what's limiting the top speed is mechanical friction. All that you see is bigger sparking. I don't know if you can see sparking, but it still doesn't run that fast, okay? Maybe it will be more, let's do it at a lower speed, maybe it will be more evident. But if you take a power tool, no, it's limited by friction. Remember, any friction, not just air friction, in this motor will require a minimum current, and a minimum current will determine some minimum K. And the moment there's a minimum K, it's like a shunt wound or compound wound. Because the moment there is a minimum current because of friction, the B cannot drop because the I doesn't drop, and then it stabilizes. But if I took a bigger motor where the friction is not significant, it will keep running faster and faster. And I think the best example is if you take at home your power saw router, and if you don't load it, it'll make a very, very high-pitched noise, which you can roughly guess the RPM from that. Okay? Another good example, there are these little tools made by Dremel, like a little router, a handheld router to do fine woodwork, and they run at a terribly high speed when they are not loaded because there is a small air streamlined motor inside. Now, one reason this motor is so inefficient because it has very big air gaps. Because if you go back to what we talked about actuators, the B is not only a function of current, the B is also a function of the air gap. So just to remind you what we derived in actuators, when we had an electromagnet with an air gap X, okay, the B was actually inversely proportional to this air gap. So the same is true for a motor. So the B was proportional to 1 over X, because B, as you recalled, was magnetomotive force divided by reluctance, and this was Ni, and the reluctance was proportional to the air gap, assuming rheostat. The battery is a resistor. Now, this power is about 1% of the total power of the motor. So by changing this 1%, you can affect the rest of the motor. For example, if you double this current, the B will double, so the speed of the motor will go down to half, and the torque will double. So if you wanted to change the speed of the motor many years ago, the simplest way was to control the power of the field, because the K is proportional to the current here. Okay? And if you start thinking about it, this is actually an amplifier. Because by controlling a few watts here, you can control hundreds of watts in the output. So it turns out that this was one of the earliest amplifiers before people had amplifiers. And there were actually complex schemes of connecting motors together just for the purpose of generating amplifiers. Okay? So imagine if this is a motor driving a generator. If you have a motor driving a generator, this is motor, this is generator, and you put in some DC power here, and you can control the field of this motor. Okay? What you have is an amplifier. The amplifier can generate many kilowatts, because here you control with a small current the output speed, and the output speed controls the output voltage of the generator. So today when you look at it, it sounds crazy, but it turns out that this idea was the most popular power amplifier there was 50 years ago. There was no other way to amplify kilowatts except by doing this. Okay? So does everybody understand why a DC motor, if you control, or DC generator motor, when you control the field separately, it's actually a power amplifier? Okay. This was called Ampli-Dyne. And these were made as huge machines, 100 kilowatt machines, because when you had, for example, a steel rolling mill, so you had to change the speed of hundreds of motors, and there was no other way to do it, except by using amplifiers like this. Okay? So today it's not used, but this idea of separating the field, that's still used today. If you have a big industrial motor and you want to change the characteristic of the motor or change the speed, that's used today. For example, I don't know if you know, there are many electric forklifts. Forklifts either have a gasoline engine or an electric engine. The electric forklifts still work like that. The Vancouver buses, which are electric, work like that. You know, many of the Vancouver buses are electric. You see them with the wires. And they all control it like that. These original ones are DC. I'm pretty sure the new ones too are DC motors, and that's how they are controlled. Okay, because you don't see any big electronic switching here with the process. Just, at least in the older ones, there was actually a big handle which controlled the resistor. In the trolley buses, you can see. The new ones maybe are electronic already. But I still remember buses here with controllers like this. So it's still used. Okay, we'll cut it off here.